Hey guys, today we're still talking about conics, but we are going and moving on about how we identify a type of conic section given a general form equation. And what's going on down here in this little picture is we have our two double napped cones, and they're stacked on top of each other, and there's a plane cutting through those cones, and it's forming all of those shapes that you've seen. So we have, if it is intersecting at just both of them, you're going to have that hyperbola. If you intersect directly perpendicular, you have a circle. If you cut it at an angle, then you have an ellipse. And then if you cut it at an angle that goes through the end of it, then that's when you get the parabola. And that's kind of what that picture was showing. So if you want to rewind and rewatch that, that would be a good idea. Okay, so these are the general forms of our conic section. So we have this giant long one, and then you have all of these that you've seen before. So again, these are regular formulas. You've seen them all before. You can use this formula chart when you're trying to plot points, etc. But these are the standard forms that we're used to graphing with. Now the thing we're going to see today is when they don't give it to us and look exactly like these guys, how can I tell what type of conic section it is? So it says the following examples that are in the general form of each of the conic sections. So if I look here, I have all of these are circles. I'm telling you right now, all of these are circles. And if you look at them for a second, you're going to notice a couple of things. First of all, they all have an x squared and a y squared term. And those numbers in front of x squared and y squared are the same. So if I look at this formula, those are a and c. So in this case, a equals c. The coefficient of your x squared term is the same as the coefficient of your y squared term. Okay, so these guys are all ellipses. Again, I'm telling you, these are all ellipses. And again, they all have an x squared and a y squared term in them. And the thing to notice here is that a and c are not the same. So a does not equal to c. So, but the thing that they do have in common is that they're the same sign. So they are both positive or they're both negative. So a and c are not the same. The numbers in front of your x squared and y squared are not the same, but they do have the same sign. They're both positive or they'd both be negative. Now parabolas are pretty easy to spot, because if you look in here, I have a y squared but no x squared. I have an x squared but no y squared. So on and so forth. So parabolas are only one squared term, which is nice. And then finally you have your hyperbolas, which if we're looking at them, again, they have all of the x squared and y squared terms in here. But if I look, this x squared was positive, this y squared was negative. X squared was negative, y squared was positive. So in these, a is not equal to c again. But the really important thing to see here is that one squared term is positive and the other is negative. They have opposite signs. And the big thing that we also have to remember when we are trying to graph these is we know how to graph all of those equations in the standard forms that we looked at. We know this is what the A does, this is what the B does, H and K, all of that stuff. So if you're given an equation of something in standard form, what you're going to have to do is complete the square in order to graph it. And we will go over this in class. But if you want to remember how to complete the square, that would be a great idea. So that way you know what to do once you know it's a parabola, hyperbola, etc. Okay, and that could also help you identify if you could then see it look like the regular standard form. The other thing that we can do with conic sections is we can identify the points of intersection. And so these can get a little bit tricky, but basically what these are is like a system of equations. So there were lots of ways we could solve systems. We could use substitution, we could use elimination, we could try to graph it. And if you're trying to do this algebraically, you're going to want to stay away from your calculator, and this will help you with your project. And so the two that we really want to try are substitution or elimination. Now substitution is going to come in handy when you have a parabola most of the time. So when I see something that only has one squared term in it, we'd want to try to substitute. So if I look at this set of equations, I see that the second one only has the x term in there, and so I want to go ahead and use substitution. And in order to use substitution here, I'm going to have to solve for that not squared term. So if I solved this equation for x, I would subtract 2 and add 2y squared. So I would know that x is equivalent to 2y squared plus 2. So all I'm going to do here is wherever I see x in my other equation, I'm going to plug in that expression. So I'd have 2y squared plus 2, and then since it was squared, we're going to put a squared on the outside, plus 4y squared minus 4 equals to 0. Now, since this is all in one variable, it's a very straightforward algebraic way to solve it. So you would go ahead and use FOIL right here, or draw your box. Remember, this is 2y squared plus 2, and that's 2 of them. So you have to use FOIL right here. If you use FOIL, you get 4y to the 4th minus 8y squared plus 4. Then I have plus 4y squared minus 4. And I'm just going to go through this algebraically. My first thing I notice is that my 4's cancel. I'm going to add my like terms together. So I have 4y to the 4th minus 4y squared. I'm going to factor out my common thing in there, my GCF, so I can take out a 4 and I can take out a y squared, which leaves me with y squared minus 1. I'm going to see if I can factor any further, and I can. This is a difference of squares inside those parentheses. So you'd have y minus 1, y plus 1 equals 0, and then you can just use your zero product property or set each of your factors equal to 0. So 4y squared equals 0, y minus 1 equals 0, and y plus 1 equals 0. So I would know all of the y values then that correspond to solutions of this system. Because remember, what I have going on here is I have an ellipse, and then I have a sideways parabola, and I'm trying to find all the points where they're touching. So when I look, I know that y would be at 0. If I add 1 here, that would be 1, and then at negative 1. So if I want to find the exact points of intersection, all I've got to do is plug these y's back into one of the first equations. And the easier one to plug into is the second one, because all I've got to do is just square the y and then solve that for x. So I could actually use the one that I've already solved. So if I have 2 times 0 squared, that's 0 plus 2. So this point would be at 2, 0. Okay? And then the other thing that I have here, shouldn't that be minus? That's interesting. This should probably be a minus in the middle. Yeah, watch me do all that math wrong. That's kind of funny. Okay, and so this one is actually a negative 2 then, because I'd have 0 minus 2. Oof. And then if I plug in 1 into that equation, I'd have 2 times 1, so 1. So 2 minus 2 is just 0, so my other point would be at 0, 1. If I plug in negative 1, the same thing's going to happen. Negative 1 quantity squared is going to get you 1, so I'd have my other point at 0, negative 1. The hardest part about these is that they tend to, you pop out a y instead of an x, and so you have to watch what you're plugging back in order to find those points. The other thing is, if you couldn't get this to factor, you'd have to use the quadratic formula or another method in order to solve it to find those exact values. Okay, the other way that you can solve these is to do elimination. And back in Algebra 1, this was probably your favorite, because what I'm going to do here is I'm going to see if I can get something to cancel out just by adding my two equations together. And if you can't get it to cancel right away, remember, you can manipulate your equation in such a way that I'm going to multiply through by a number or a sign and make things work. So if I notice here, if I add these two equations together right as they are, I have x squared plus x squared, which gets me 2x squared, but y squared minus y squared goes away. Then what I'm left with, there's only the 16x term, and then 39 plus negative 9 is 30. I'm just left with an equation in one variable, and I can go ahead and use all of my factoring and stuff in order to solve this. So I could just take out a 2. I can factor this guy using my box or 4-term grouping, but I know the factors of 15 that add up to negative 8 would be negative 3 and negative 5. Set each of my factors equal to 0. So I'd have x minus 3 equals 0, so one of my zeros is 3. X minus 5 equals 0, the other one is 5. So now I have my two intersection points, but I've got to go ahead and plug them back into one of my equations. I tend to plug into the one that has lesser numbers, just so it's less scary. So if I plug in 3 into the equation x squared minus y squared minus 9 equals 0, I know that I have 3 squared is 9 minus y squared minus 9 equals 0. Well, those go away, so I know that y has to be 0 there. So one of my intersection points is at 3, 0. If I plug in 5 into that equation, I'd have 5 squared, or 25, minus y squared minus 9 equals 0. That gets me 16 minus y squared equals 0. Subtract 16 from both sides. That would be a negative 16. So if they're both negative, I divide both of them by negative 1. So I just have to take the square root of 16. Hard part here, don't forget that the square root of 16 when you're solving an equation is plus or minus 4. So one of my intersection points is going to be at 5, positive 4, and my other one's going to be at 5, negative 4. So whenever you're solving with the square root method, which no big deal, you can totally solve a lot of these with the square root method, you've got to remember to put your plus or minus in front, otherwise you're going to lose some of your intersection points. Because if you checked this on the calculator, like you could graph on Desmos or whatever, you would have two circles intersecting, and so those two circles are going to hit at three different points. Okay, and hopefully that will help you out with your project. Again, sorry I messed up over here, but you're going to use those methods that you use to solve systems of equations in order to solve these guys. You have substitution or elimination are the best practices when you're trying to solve with algebra. And again, if you get ugly numbers, that's okay. Just leave them as a square root or as a fraction.